This is a discussion for experiment 15 in chemistry 1B, which is on thermodynamics of a solution process. In this lab, we want to determine the delta H naught and delta S naught for a reaction, and also determine the delta G naught and the KSP at different temperatures for a reaction. And so the reaction that we're looking at, I mentioned, was a solution process. Well, it is dissolving potassium nitrate in water. So we have a potassium nitrate on the left as a solid, and then on the right, the potassium ions and the nitrate ions. And so we can write the equilibrium expression, in this case called the KSP, as the concentration of potassium ions times the concentration of nitrate ions. And since we're talking about dissolving potassium nitrate in water, this is equal to S squared, where S stands for solubility, not entropy in this case.
And we have learned that we can relate delta G naught to K, and delta G naught is negative RT, natural log of the K, in this case, the KSP. So you can see in this equation that delta G naught and KSP are temperature dependent. And in this equation, R is equal to 8.314 joules per mole Kelvin. So we will calculate the solubility at different temperatures, which gives us KSP at different temperatures, which gives us delta G naught at different temperatures. But we also want to calculate delta H naught and delta S naught for this reaction, and these are temperature independent. And so we actually have two equations for delta G naught. The one that I just wrote up on the last slide, delta G naught is negative RT ln of K, or in this case KSP. But we also know that delta G naught is equal to delta H naught minus T delta S naught. So we can see those variables, those thermodynamic properties in that equation we want to solve for. So these both equal delta G naught. So I'm going to replace delta G naught in the second equation with negative RT ln of KSP. And that equals delta H naught minus T delta S naught. So I'm going to rearrange a little bit, dividing each side by negative RT. And that gives us the natural log of KSP, because they are negative RT cancels out. So we get natural log of KSP on the left side of the equal sign equals negative delta H naught over RT plus delta S naught over R. The temperature canceled out on that one. This can be rewritten again as natural log of KSP is negative delta H naught over R times 1 over T plus delta S naught over R. And this is what's called the Van 't Hoff equation. And it is in the form of y equals mx plus b. We can graph some data in a certain form if we look at the equation, and we should get a straight line. So y is the natural log of KSP, so that's what's going to go on the y-axis, and 1 over t in Kelvin is going to go on the x-axis, and that gives us a straight line. So I'm going to rewrite this equation here. Natural log of KSP is equal to negative delta H naught over R times 1 over T plus delta S naught over R. So again, this is in the form of y equals mx plus b. So y equals mx plus b, I'm going to write right under that equation. So I'm going to draw some axes. And so I have the y-axis and the x-axis. So on the y-axis, we want to put natural log of KSP. And on the x-axis, we want to do 1 over T and 1 over Kelvin. So this should give us a straight line, which I'm going to draw here. I'm going to start by drawing a positive slope. And so the slope, if we look at the equation, is equal to negative delta H naught over R. And so I have a positive slope, and this means that for a positive slope, it would be an exothermic, because a negative delta H naught times the negative sign would be a positive slope. So here, a negative slope, the slope equals negative delta H naught over R, this would be an endothermic, because a negative times a positive delta H gives us a negative slope. In each case, the y-intercept is equal to delta S naught over R. So from the equation, we can see that B, the y-intercept, is delta S naught over R. So if we have a graph and we are able to get the slope and the y-intercept, we can solve for delta H naught and delta S naught. So you're going to determine the solubility of potassium nitrate at different temperatures, because that will give you your KSP, which you need to take the natural log of to graph as a function of 1 over T. Then you can determine, like I said, the KSP, and then you can do your graph in Excel, so that way you can solve for delta H naught and delta S naught. In order to make the plot, we need to calculate the KSP at different temperatures. And to get the KSP, we need to determine the solubility of the potassium nitrate at different temperatures. So how are we going to determine the solubility? Well, what we're going to do is we're going to take a graduated cylinder and we're going to put about 12 grams of potassium nitrate in that graduated cylinder. And we'll make sure to record the actual mass that we use. Then we'll add about 9 milliliters of deionized water. And at this point, it's not going to dissolve because that's a lot of solid and very little water. So we're going to put it in a big beaker that's on a hot plate. And so we can heat it up so that way it dissolves. So we're going to heat to dissolve that solid potassium nitrate in the water and make a solution. And once we make that solution, we can record the volume of the solution. So it's going to be greater than 9 mils because we've added a lot of solid, 12 grams. So we'll call it the actual volume. We're going to want to take that graduate cylinder out to record the volume. And also we're going to take it out because we want to see when crystals first start to form and what temperature that's at. So there's a temperature probe in that graduated cylinder that's hooked up to the computer. And we are going to look for the first formation of crystals, because right when those crystals form, that's essentially the solubility, all right, of the potassium nitrate. So we're looking for the first appearance of crystals, and we're going to look carefully, and we're going to see those crystals, and we're going to hit keep on the computer as soon as we see them to get the temperature at which we saw those crystals. So this means we have a saturated solution at this point, and we're going to get the temperature at this point. So the temperature for our value of this saturated solution. And for our KSP, we need the concentration of potassium, the concentration of nitrate. They equal each other. And we get that by taking the moles of potassium nitrate divided by the volume of the solution. So the moles of potassium nitrate come from the mass that we record. We can convert that to moles, of course, using the molar mass. And then the volume of the solution in liters is in the denominator. So we can get the concentration and then the KSP. All right, so we can calculate these values, which represent the solubility. And then KSP is the solubility squared. So we're going to go ahead and repeat the process. We're going to take that graduated cylinder that we saw the crystals in. So we have crystals in there. And we're going to add about 3 mils of water. And then we're going to heat it again to dissolve those crystals. Right, so we want to get a solution again. So we heat it, we take it out. And so those crystals have dissolved. We record the new volume, right, because it's going to be a new volume since we added 3 mils of water. And we are going to, again, have our temperature probe inside that solution where we can monitor the temperature, and we're going to look for those crystals. And as soon as we saw the first appearance of crystals, we are going to hit keep on Logger Pro in order to get the temperature of crystallization for this new solution. Right, so that's going to be in our degrees Celsius. So we can calculate the concentration of potassium and nitrate in this new solution, right? We know potassium concentration equals nitrate concentration, and that equals the moles of the potassium nitrate divided by the volume of the solution, just like we talked about before. In this case, the moles of potassium nitrate's the same, right? We haven't added any more potassium nitrate. We haven't taken any out. That's the same. It's the volume of the solution that changes, right? We're adding more water to it. Okay, so we're going to have a different concentration of potassium nitrate. So we're going to get a different KSP at each different temperature. So it corresponds to a different temperature. So overall, we're repeating the process of dissolving and looking for crystallization a total of 8 times. So we're going to have 8 different data points that we will have to make our Van 't Hoff plot to calculate delta H naught and delta S naught.